Heat shock proteins are something else that I wanted to talk about. These are also things that are involved in protecting from severe changes in temperature. Not in this case, this has to do with more rather than with freezing. It has to do with heating. But when cells are exposed to elevated temperatures, their function as molecular these proteins also function as molecular chaperones, and which is what I was talking about before. And there are a number of these different kinds of heat shock proteins. There's an organism called the Madagascar periwinkle. This is something that you would find in the littoral zone, and this produces a heat shock protein that's called HSP90. The designation 90 means that it has a molecular weight in the range of between 90 and something less than 100 daltons. That's 100,000, basically having an atomic mass of 100,000. So this particular one actually, although it's called HSP90, it's an 817 amino acid protein that has a molecular weight of 93,491 daltons. So that's basically a fairly kind of an average size protein, but it does have a chaperone role, and its role is in assembly and processing of cell wall components. So there are other proteins that are also involved in these kinds of heat and cold processes, and there's another one that is actually also probably in addition to trehalose, which is not a protein, but there is something called thermal hysteresis proteins, and what these do is they actually have a non-colligative depression of water's freezing point. What that means is, when we say it's non-colligative, colligative properties are properties that actually depend on the number of particles that you have in solution. So when we talk about things like freezing point depression, we know that if we throw salt into water, we can depress the freezing point of water. And that is a colligative property. And the more salt we throw in, the more the freezing point is going to be depressed. In a situation like this, where we've got a non-colligative depression, it doesn't really depend on the number of particles that we have. But what actually happens is, let me see if I can draw this, is if you had a surface that, let's say we had a block of ice that was forming, or some ice that's actually forming inside of this cell, and this is normally going to be deposited kind of in sheets. What happens is these thermal hysteresis proteins, they actually distribute themselves on the surface in a fashion sort of like that. And what happens is that actually disrupts the formation of a water layer. And this, you get kind of a curvature up here. So you don't really get a water layer, and it actually prevents formation of ice crystals inside the cell when that happens. There are a lot of different thermal hysteresis proteins, and the different ones bind to actually to different crystal faces within the water molecules. So they form what are called bipyramidal crystallites. So it's like a pyramid on either side, and this inhibits the growth of large ice crystals. Ice crystals can be very, very dangerous inside the cell. There are also antifreeze glycoproteins and antifreeze proteins. So again, these are just specific proteins. The antifreeze glycoproteins, for instance, there's an example here where the protein actually is just a repeating a repetition of 3 units: alanine, alanine, threonine, and this repeats over and over and over again: alanine, alanine, threonine. And the threonine is modified by having a disaccharide residue, which is beta-D-galactosyl D-N-acetyl galactosamine. So this again, these are 2 sugars one of which is modified with an amino group, and they're actually attached to the threonine molecule. And again, these things actually function literally as antifreeze, so that the cells are actually, when temperature gets very, very low, ice crystals don't actually form within the cell, even though the temperature is below the freezing point of water. So these are all forms, these are all ways in which these various cellular components can be used to prevent things like cell lysis that would occur normally during the freezing process, damage to organelles, and during the dehydration process. We've got the tree halose to prevent damage when water is lost from cells. And we've got a couple other molecules here that I wanted to show you that are also actually involved, that may be involved in protecting organisms during particularly sensitive developmental periods. So the two molecules that I'm going to show you here, the one on the top is what's known as a sesquiterpene. Let's see if I can illuminate this. I'm having a lot of trouble getting light in here. I don't know why. That's a little bit better. So the one on the top is as I said before, is what we call a sesquiterpene. If you count, you would find that there are 15 carbon atoms: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 to right here. This other carbon atom here really is not part of the sesquiterpene. This is a carboxylic acid methyl ester. These things are modified in a variety of ways. There are a number of this particular kind of sesquiterpene. They're actually called juvenile hormones. And what they do, you mostly hear about them in insects, but some time ago people started looking and saying, well, insects have juvenile hormones because they undergo a series of developmental stages where they pass through larval stages, and then they'll pupate, and so they have to grow to a certain size. And you don't want the organism not to mature during this process. So the function of the juvenile hormones is to prevent the organism from suddenly becoming an adult. It has to grow to a specific size. So here, the way these things are modified is sometimes these CH3 groups here are CH2, CH3. So sometimes you'll actually have some of these that will look like that, and sometimes these double bonds will actually oxidize and form a three-membered ring, which is called an epoxide, and that will look like that. And you can also get one where you have an epoxide here as well. So you can get a variety of different combinations of these things, but they're all juvenile hormones. And then underneath that is a particular something associated with the juvenile hormones, which is called an ecdysone. Ecdysone. And this is a particular kind of steroid that actually is involved in the molting process. So at some point in time, the juvenile hormone would stop being made, and then the ecdysone would be expressed, and the ecdysone would actually cause the organism to molt. Well, if you look at sea creatures, you'll find out, at least among the crustacea, that many of these things, and it's not just among the crustacea, by the way, there are other organisms that also have juvenile hormones, that are also producing the juvenile hormones. But what's interesting about the juvenile hormones is that during juvenile hormone production and during ecdysone production, organisms that are in this state seem to be better able to survive desiccation. So these molecules also must have something to do with being able to enable an organism to actually survive the trauma of dehydrating. That's what we see. So, and as I said, it turns out that this particular ecdysone, which is called beta This is beta-ecdysone. And beta-ecdysone is actually found among many different kinds of crustacea, which also undergo a molt. By the way, I just want to point out to you that when you see these kinds of structures here, where you see a wedge, which you see here and here, or if you see these dotted structures here, we also saw that originally on the trehalose molecule, but I didn't mention what that is. That's just telling you that has to do with stereochemistry. That is how these groups orient themselves in space. So if you've got a wedge like this, it's telling us that the hydroxy groups are above the plane of the molecule, and if we've got a dotted line or sometimes a hatched, sometimes it's used as a hatched wedge like that, that's telling us that these groups are actually going below the plane. So this hydroxy group is pointing down. These two hydroxy groups are pointing up. Okay.